Today we are going to learn about Kubernetes Pods, deep dive and best practices. This video will teach you how to configure, scale, and optimize Kubernetes Pods for various workloads.
Welcome to our educational journey into Kubernetes Pods. As the core building blocks of Kubernetes, pods are essential for deploying and managing containerized applications. In this video, we will explore the intricacies of pods, including their lifecycle, configuration, and best practices for optimal performance. By the end, you'll have a comprehensive understanding of how to harness the power of pods to scale and manage your applications efficiently.
To effectively manage Kubernetes pods, understanding their lifecycle is crucial. The lifecycle consists of several phases: pending, running, succeeded, and failed. Each phase represents a specific state in the pod's existence. A pod starts in the pending phase, waiting for resources to be allocated. Once resources are available, it transitions to the running phase, where your containers are active. If a pod completes its task successfully, it enters the succeeded phase. However, if an error occurs, it moves to the failed phase. These transitions are triggered by events like successful container startup or resource allocation failures. Managing this lifecycle involves using tools like Kubernetes to analyze pod status and troubleshoot issues via pod events. These insights aid in optimizing resource utilization and ensuring application reliability.
Configuring Kubernetes pods is primarily done through YAML files, which serve as the blueprint for defining what your pod should look like and how it should behave. The YAML file contains specifications such as the container image, resource requests, and limits. Key fields include metadata, spec, and containers. Within the spec section, you specify details such as container names and images, along with ports and volumes. Labels and annotations play a critical role in organizing and managing pods. Labels are key value pairs attached to objects that help in selection and querying, while annotations provide metadata that can be used by tooling and libraries. YAML configurations can be dynamically updated, allowing for efficient management and scaling of applications by simply applying changes to the existing YAML files.
Multi-container pods allow you to run closely related containers together, enabling efficient communication and coordination. This design is particularly useful for implementing common patterns like sidecar, ambassador, and adapter. The sidecar pattern is used for auxiliary tasks such as logging or monitoring, whereas the ambassador pattern helps in communication with external services. The adapter pattern is used to standardize and transform data formats. Co-located containers can share storage and network resources, leading to reduced latency and improved performance. Implementing multi-container pods requires careful planning to ensure that containers are appropriately configured to work together harmoniously. This setup can significantly enhance the functionality and flexibility of your applications, making it easier to scale and manage complex workloads. Replica sets are crucial for scaling Kubernetes pods, ensuring that a specified number of pod replicas are running at any given time. They define the desired state for your application, automatically creating or deleting pods to match the desired count. This mechanism provides automatic failover and recovery, enhancing the resilience of your applications. Horizontal scaling, achieved by adjusting the number of replicas, allows for greater flexibility in handling varying loads. Managing replica sets is straightforward with Kubernetes, where simple commands can increase or decrease the number of replicas. This scalability ensures that your applications can handle increased traffic seamlessly, maintaining performance and availability.
Effective networking in Kubernetes allows pods to communicate with each other and with external services. The Kubernetes networking model provides each pod with a unique IP address, facilitating direct pod-to-pod communication. Services and DNS are used for service discovery, enabling pods to locate each other through stable endpoints. Network policies are crucial for securing pod communications by defining rules that control the flow of traffic between pods. Troubleshooting network issues requires a deep understanding of these components, along with tools like Kubernetes and network plugins. By mastering pod networking, you ensure robust and secure communication within your Kubernetes cluster, enhancing the overall reliability of your applications. Liveness and readiness probes are essential for maintaining the health of your applications in Kubernetes. Liveness probes determine if a pod is running, allowing Kubernetes to restart it if necessary. Readiness probes, on the other hand, indicate if a pod is ready to accept traffic. Configuring these probes involves specifying criteria like HTTP endpoints or command executions in the pod specifications. These checks help in detecting failures early and recovering from them, thus maintaining high application availability. Best practices include setting appropriate thresholds and timeouts to avoid unnecessary restarts. By implementing effective health checks, you can ensure that your applications remain robust and responsive, even in the face of unexpected issues.
Resource management in Kubernetes involves configuring pods with appropriate CPU and memory requests and limits. Resource requests specify the minimum resources a pod needs to run, while limits define the maximum resources it can consume. These settings prevent resource contention, ensuring that pods have access to the resources they need without impacting other pods. Optimizing resource utilization is key to achieving efficient performance and cost effectiveness. Monitoring tools, such as Prometheus and Grafana, can help visualize and adjust resource allocations based on usage patterns. By mastering resource management, you can maintain a balance between performance and efficiency, ensuring that your applications run smoothly and cost-effectively.
Designing Kubernetes pods with best practices in mind is essential for achieving scalability, resilience, and security. Start by organizing pods using labels and selectors to facilitate efficient management and scaling. Implement effective logging and monitoring to gain insights into pod performance and troubleshoot issues quickly. Security should be a top priority, with measures like network policies and pod security context to ensure compliance with organizational standards. Regularly reviewing and updating configurations helps maintain alignment with evolving application requirements and Kubernetes updates. By following these best practices, you can create robust, scalable, and secure Kubernetes pods that enhance your application's overall reliability and performance. In conclusion, understanding and managing Kubernetes pods is vital for any successful deployment in a Kubernetes environment. We've explored various aspects of pods, including lifecycle, configuration, scaling, and best practices. These skills are essential for ensuring your applications are robust, scalable, and efficient. We encourage you to delve deeper into Kubernetes and explore additional resources to expand your knowledge. Thank you for joining us on this educational journey. We hope you found it insightful and engaging.